finish up chapter 26 in this video. It's going to be chapter 26, section 6, and it deals with multiple slits and diffraction gratings. The good news is if you can do twin slit interference, multiple slits are not any more difficult. In fact, the formulas are identical. If we go back to the second section, we found out that constructive occurrence for two slits, this was our two slit rules, occurred when d sine theta was m lambda, and of course destructive occurred when d sine theta was m plus a half times the wavelength. Okay. And we got a pattern that looked like this. There's m equals 0, m equals 1, and there's the other m equals 1. And you notice that in between those maximums, there's exactly one minimum. What happens if we use multiple slits? Let's suppose that we use 8 slits instead of 2. 1, 2, 3, 4, 5, 6, 7, 8. Now that's not perfect, but we get the idea. I wish they were perfectly spaced. I have 8 sources. There's going to be a point, some point. I'm going to draw a point right here. Let's suppose that's a place where there's constructive interference. One, 2, 3, 4, 5, 6. Okay. So there's points where all 8 of those slits combine and produce one of our bright spots. But in between those points, what we find is there's not just one minimum. In fact, there should be a bright spot right here where the other, that's the central. This was the central, and this might be the first. There'd be another one down here. But in between, rather than having one minimum, there would actually be 7 minimums if I have 8 different slits. And so my pattern comes out looking more like this. We put our 0 here, and we put our other one here. So we have our bright, but it comes down really sharp. There's 1 minimum, 2 minimums, 3 minimums, 4, 5, 6, 7, and then we get our peak and more minimums. 1, 2, 3, 4, 5, 6, 7, peak. And the result is, and this probably isn't drawn, these get much narrower and sharper. So there's an advantage to using lots and lots of slits. There's something called a diffraction grating. And those of you that may have had me before for class, you may remember those glasses that we used in the lab for optics, where you could look at the light fixtures in the room and it looked like a rainbow. Those were diffraction glasses. Diffraction gratings and glasses are made not with actual slits through the material, but they put scratches or markings on them. If you have a DVD or a CD player, it can act like a diffraction grating. Okay, so Write this down for you. Fraction gratings are described, let's see, are an array of a large number of parallel slits. And they're really usually not any slits. Usually just grooves on a piece of glass, or possibly some other optical material, like a piece of plastic. The diffraction gratings that we had in the lab were just had the little paper frames and little plastic lenses. We describe them by the number of lines per width. So for example, you may have a diffraction grating that says it is 600 lines per centimeter. That means in a 1 centimeter space, there's 600 of those grooves or 600 lines. Generally, if we're looking at a diffraction grating for the visible spectrum, they're going to be anywhere from, say, 500 to 1,500 lines per millimeter. I cannot hardly even imagine how one can get 1,500 lines etched into a piece of glass in a 1 millimeter spacing. But they can, and that gives us things that are on the order of a wavelength. This is how we describe them, but if you'll remember, our formula uses d sine theta. Well, d is the distance between slits. So if I want to find d is the reciprocal of the line spacing. So d, which we've used before, which is the distance between slits, is the reciprocal of the line spacing. So for example, if we are told that we have 1,200 lines per millimeter, then D is equal to 1 millimeter for every 1,200 lines. So we know 1 millimeter is 1.0 times 10 to the negative 3 divided by 1,200. So if I put that in a calculator, I realize that my line spacing is 8.33 times 10 to the negative 7, or 833 nanometers. Now that's not quite as small as a wavelength of visible light, but it's close. Visible light is on the order of 400 to 700 nanometers. So it's the same order of magnitude. All right, let's do an example. We know that visible light is 400 to 700 nanometers. That's the wavelengths for visible light. They want us to find the first order, let me rephrase it. Find the angular width of the first order spectrum produced by grading that's 600 lines per millimeter when white light shines on. Okay, we know that white light contains all the colors of light, and we also realize that where your central bright spots are depend on the wavelength of light. So the location of red light that has a wavelength of 700 nanometers is not going to be the same location as the bright spot for violet light down here at 400 nanometers. They're going to have different locations, and they'll actually be at different angles. And so they want us to find that angular width, or that difference between the angles. We need D. So D is going to be 1 millimeter for every 600 lines, or 1.0 times 10 to the negative 3 divided by 600. That's going to tell us the spacing between the lines. So D comes out to be about 1.67 times 10 to the negative 6 meters. So there's our line spacing. There's D. Our formula says that D sine theta equals m lambda, or sine theta equals m lambda over D. So I just want to find that angle for both red light and for violet, or I can even rewrite this as theta equals the sine inverse. I'm going to use m equal 1, so it's just going to be lambda over D. So for red light, it's going to be the sine inverse. The wavelength of the red light is the longest wavelength, 700 nanometers, times 10 to the negative 9. D is 1.67 times 10 to the negative 6. And I get that angle for red light is about 24.8 degrees. Notice that the longer wavelength is going to give us a larger number, so we're going to get a larger angle. If I do the same thing for violet, it's exactly the same, only now I have 400 nanometers. So now when I do that sine inverse, I get 13.9 degrees. If I want the angular width, that's a difference. I just need to subtract those. So that angular width, delta theta, is 10.9. Okay, so that's the first part of that example. There is a second part. The second part says, show that the violet end of the third order spectrum overlaps the red of the second order spectrum. So let's think about that. Let's find the location. If I want the second order for red, I'm going to have to put a 2 here, and that'll be the only difference. So if I put in that 2 there, 2 times 700, so this is the second order, because what happens when you look through a diffraction is you'll see a rainbow, and then you'll see a second rainbow, and then you'll see a third rainbow as you're looking through those classes. That first one from the central, that's the first order spectrum, then the second order, then the third order. So if I put in this 2 here and I get the location of the second order spectrum for red, it's at 57.1 degrees. That makes sense. The first order location was only 24.8 degrees from the central line, and this is at 57.1 degrees from the central line. But if I do the third order one for violet, so that means I'm going to have to put a 3 in here, times 3. When I do that third order one from violet, it's at 46.1 degrees. So even though this is a third order spectrum and we would expect it normally to be farther from center, we see that the third order for violet is not as far from center as the second order from red. So those spectrums are going to have some overlap. If you think of, here's the central line, and it's going to go violet to red, violet to red, violet to red. What you're going to see is it actually overlaps. And the third one starts at 46.1 degrees, even though the second rainbow doesn't really end until 57.1 degrees. Okay. That finishes up chapter 26 on diffraction and interference patterns. That also finishes up all the new material for the course. The rest of the videos I'm going to post are going to be reviews. We'll go back and look at electricity and magnetism and some of those topics from earlier in the semester.